Okay, just a few additional notes on thermodynamic processes. We've talked about a few so far, but we're going to use the term quasi-static process. Quasi meaning that it's not really, but it comes close to being a stationary process or an unchanging process. And the reason why we call it quasi-static is when we're doing expansion and compression of these ideal gases, we're doing it at such a slow rate that we don't get any disruption of the thermodynamic equilibrium. We want to allow compression and expansion to happen so slowly that at all times our system remains in thermodynamic equilibrium. What I mean by that is every part of the gas is at the same pressure, every part of the gas is at the same temperature, every part of the gas is at the same density. So all these state variables remain constant throughout the process. Now, in the real world, this is not possible. When we allow a gas to expand or we compress a gas, we will get some regions that heat up more than other regions, okay? We're adding heat to the system. Well, what part of the system is going to get warmer? Obviously, the part which is in contact with the thermal reservoir, okay? Those further apart are going to be at a lower temperature. Also, as the piston moves in this particular case, we are going to get the gas moving in such a way that turbulence will result. So let's say this were an internal combustion cylinder, the piston moving, okay? If you were actually to watch this, you would see that the temperature would not be even and that there would be quite a bit of turbulence in there. And in fact, this would lead to lower efficiencies. Again, we are dealing with approximations. We are trying to come up with an approximation of how these systems will behave. But again, you'll hear the term quasi-static. Obviously, you know, we can't move these cylinders so slow, so infinitesimally slow that no work will come out of the system. There has to be some motion. There will be a little bit of turbulence. There will be a little bit of non-equilibrium thermodynamics going on here. But we try to get it as close as possible. Okay, so again, while it's not possible in real systems, some systems do change slowly enough that the equilibrium is nearly met. And the quasi-static processes that we're most interested in are the ones that we've talked about so far: isobaric, isovolumetric, isothermal, and adiabatic. Okay. Now, isobaric, we've already come up with an expression for work. Work is equal to pressure times delta V. Isovolumetric, that's easy. The work is always zero. Okay. Isothermal, a little more complicated. In RT, natural log VF over VI. And when we get to the adiabatic, we're going to say that the Q, heat added is zero. So there the work is just going to be equal to the change in the internal energy, or the negative of the change of the internal energy. In real world processes, the amount of work that we'd actually get out would be a little bit lower than this, okay? Same thing through the isothermal, probably the same thing with the adiabatic. But again, as long as we allow these processes to go forward, you know, slow enough, we will approximate these quasi-static conditions of thermodynamic equilibrium. It's important for you to be able to identify the different trajectories on the pressure versus volume diagrams for these different processes. Remember, anything vertical, okay, there's no area underneath this, so that is always isochoric or isovolumetric. All right. The other easy one is the horizontal line. Okay. Going horizontal where the pressure is constant, we're just changing volume. That is isobaric. If we're following the isotherms of constant temperature, that's a C right here, isothermal. And then adiabatic, because no heat is being added to the system, it's a little bit different. Okay. During expansion, we lose some energy internally. So we drop from a higher isotherm to a lower isotherm. So again, it's important to be able to recognize those on the pressure versus volume diagrams. The cyclical process, we're going to put all of these together to create one complete thermodynamic cycle from which we can extract energy from. Going back here, we're going to want to allow the gas to expand when the temperature is hot, and we're going to want it to compress when the temperature is cold. Okay, it's not going to quite look like this. More likely, when we put the different thermodynamic processes together, like for instance, I could do an isobaric expansion. I could do an isovolumetric drop in temperature. I could do an isobaric compression. And then I could do an isochoric increase in temperature. That would be a more typical look for a curve, a thermodynamic cycle. You'd actually have, 4 different processes going on here that we put together, and the work enclosed in this curve would be equal to the total work done by a thermodynamic cycle. Okay, but again, the general form for the work done by a thermodynamic cycle, we're going to start from one point, go all the way around, and return to that point. Okay, our initial and final position here are going to be the same. The total work done during one of these cycles is going to be enclosed in this right here. So we can imagine, let's say I have some cylinder piston, right? Maybe it's a internal combustion engine. But in any case, the cylinder piston can move up and down, right? So here it's expanding, so the cylinder is moving upward to this point, and then it starts going down, okay, and compresses again. Every time that cylinder would fire, that would be one complete thermodynamic cycle.